Alright, we're gonna do a little side quest here. We're not gonna go live because right now our bandwidth really sucks. And anyways, Jacob Moga gave me something, so I'm gonna check this out and try to write this out and kind of see what this all is all about. He said it was C code, so I write C code, so let's kind of throw this together and indent this in a pleasing way. I don't know if it lost its indentation when he kind of pasted it from the Facebook chat, but, you know, indentation is nice. So we're just gonna kind of break this apart until it starts to be in a little bit more sensible of a manner here. So, we got this int floor, whatever the heck. That looks like another component of, God, I wish my editor, when my editor goes off its edge, it does not wrap gracefully. So this is another reason why I like very strict column limits. But yeah, we got this plus, and this is like another thing. Okay, so we can take this thing here, and anywhere we see one of these clusters, we're going to be like, put a plus between that, right? And then we got some craziness over here. So this is, where are you ending? You're ending right here. Okay, so this is like another kind of scope of stuff that's happening over here, right? And I'm all for extra parentheses, that's fine. Like, the extra parentheses do not bother me. It's just being able to break it apart and kind of see the hierarchy of, you know, what's going on with this transformation here. So it's like a, we call this like a 15 minus. So 15 minus this thing, right? So we're trying to keep all the math to where it's kind of like, you see like the pluses, right? So this thing plus this plus that, right? Keep all that logic kind of lined up nicely. Now, what's the next significant chunk of thing that needs to go here? I see. So it looks to me like there's one extra layer of parentheses that does not belong, as far as I'm concerned. Yeah, this is one extra layer here, it looks like. Yeah, this is an extra layer that's just hanging out there. That doesn't really belong. Maybe it was deleted. Maybe it was deleted after the case, like there was something there that used to be there that was kind of important. I don't know. Okay, so this cluster of stuff, and then this cluster of stuff here, then this cluster of stuff here, right? So, okay, cool. Okay. What about this? What's all this about? Plus, and then we group this, and this is grouped here. That's fine. So I would really like to figure out. So we got like a modulus 4 here. Modulus 4, modulus 2. So the other thing I'm going to do is these multiplications, modulus 4, y modulus 4 times 4, is that some type of stride? Like, what's going on here? And we have x plus y, so it's giving us a xy location. You know, it's an 8x8 grid, so I'm assuming that the input needs to be as an index location in an XY grid. Now, I don't quite know why he had all those weird numbers, but let's just throw this into, let's try to normalize this. So let's normalize this for a second. So he has this logic here, and what I'm seeing is this extra. Okay, that's fine. So let's go bam bam, bam bam, bam bam, Bam, bam. Okay, so let's kind of move this over. So we have this here. So what I want to do here is I want to do like a 0 minus. Or not a 0 minus, but a 0 plus. Right, and this is just me notating that, hey, there's no transformation here, but I see that there's obviously a pattern here, where we have this x modulus 4, and this is, you know, modulus 2 here, but we have the 2 and 3 here. Then over here, what I want to do is say, this is y modulus something or other times something. Does this belong on, which side does this belong on? So it looks like to me, we got this minus, pluses and whatevers. I'm not sure what side this belongs on, but it kind of looks like, you know, there's this times 4 over here. So it almost looks like, you know, 4 times the modulus goes over here, right? And then this, like, I don't know what we're doing. I don't know what this math stands for. But when I'm looking at it, it kind of looks like, hey, here's all this stuff. Now this is, there's 2 of these, so we can actually get rid of this. That's just extra junk here. Could move this back one. Actually, don't need to move it back one, do we? We could move it back one, sure. 15 minus all this stuff, right? Sure, okay. Okay. So this floor stuff, if this is indeed C code, we don't need to floor this, right? We just go y divided by 4 and we're done, right? If this is C code, y divided, there's no need for floor here. So what we're gonna do is we're just gonna say no need to floor. We're gonna call this no need to floor. We're just gonna be silly here. We're gonna say, you know, define no need to floor, and whatever. No need to floor, and just go no code. Right? Because really, we could take no need to floor. We can just remove that, right? It's just a parenthesis, right? Now we have an integer cast. That integer cast is going to do the floor for us, but it's not necessary. But sure, why not? Define no int cast. So I'm just going to change this around. No int cast thing. No, it's called no int cast. No need to floor. So this ends up getting blanked out. This just ends up being a whole bunch of extra parentheses that are just kind of there. And then over here, what we're going to do is we're going to undefine this. We gotta save this eventually. Let's call this, so that we obviously need some type of return thing here. So we could do, you know, I don't know. So it's like a int something or other. And it's an int 32. Int, I don't know, Moga Math. We'll call it Moga Math, and it takes an int x and an int y, and it's returning some type of index. I don't know exactly what this index is. And looks like we're doing this without, I think it's intentional. It's intentional that there is a return value that is just, there's no temporary values here, right? That is intentional. So we're trading the I gotta say this somewhere. We're trading memory for CPU, right? So there's a CPU memory kind of trade-off here, or like processing versus memory. if you have a lot of memory but you don't have much processing power, you can, make a whole bunch of lookup tables for things, right? And then conversely, if you don't have much memory but you got a lot of processing power, you can generate lookup tables on the fly. So this seems like some type of lookup table generated on the fly. And I don't know what all these offsets are, but if you look at this 15, I'm going to change this 15, because I just have a hunch here that that's a 16 minus a 1. And you'd be like, what do you mean 15, 16 minus 1? Like, what's the point of that 16 minus 1? Well, I guarantee that that 15 has something to do with being a power of 2, and this is some type of max coordinate value. This is some type of max coordinate value. Let's save this somewhere because this is annoying us. So in our drive, I don't know where we want to save this. Why don't we just do it in Git? How about we just put this in Git and just do new folder. It's gonna call it I'm gonna call it Moga Math. And I can delete this later, but let's just, for habit, let's just put it in here. And we'll do mm.c11, mogamath.c11. What else do we got here? What else do we need to do? Well, I have this habit. In strict C, we cannot write it like that. We gotta remove those semicolons. Int mogamath, int x, int y. Okay, so now we actually have to do this in a loop somewhere. But let's kind of indent this how we usually indent our code. So, section, Moga Math formula. So we're going to take this formula. We're going to create like a little section in our code. We actually don't need to indent this much. We can actually remove a level of indentation here. Okay. Let's give this a shot. Okay. So we got this Moga Math formula thing. And then we need like a, int main void pedantic. And then way too much stuff here. We can take the printf. We don't need this malloc and free stuff from stdlib. And our include, we should really just put that at the top. Or no, we could put it up above main. Sure, why not? Printf. I don't need that commentary anymore. For whatever and whatever. So, number equals, width times height. Let's do width times height times width times height, and the number here. So int width equals 8. 8 cells wide. That's what I saw in the diagram. Int the height is also 8, and this is 8 cells high. And this is the total number of cells, right? The width times the height. Okay, so we're gonna go through here. We're gonna print off this thing here. We're just gonna print off the I. So I equals %d, and then instead of this, it's literally just gonna be I. I don't know. We did it like that, so I, and then we want to take this Moga Math here, and Moga Math XY, let's do seeing that it's like this, let's not do indices. Or, let's do, index to xy. Okay. So we have an index to xy thing here. The width and the width here. Pixel x, this is the index, so we could do a pixel index here. Let's do this. Okay, so this is the number of pixels. And pi is the pixel index. So let's get rid of this int here. Just call it pi. And this is pixel x chord, and this is pixel y chord. Okay, so we're gonna do this pixel x equals this, pixel y equals this, and the next thing we want to do is we want to say, printf what I is, printf what the pixel index is. So, px comma py equals %d comma %d \n, then px and then py, and then we want to be like, well, what's the Moga Math? So, int mx, Moga's x, or actually, no. This is x and y in here. So really what we want is Moga index, right? So, I'm going to call it Mogdex. Moga's index, right? So this is Moga's index, one-dimensional, I think. Okay, so this is Moga's index, and we're going to do a printf. Say Mogdex and %d \n, and then Mogdex. I actually have to calculate Mogdex though, right? So to get Mogdex, we're going to take this Moga Math thing here. It takes a x and a y, so Moga Math px and py. And we'll give that a shot. We'll see kind of like what we get from that. I'm sure we've made some mistakes, so let's save this and then file new and do hkmf c11 mini. There, we got a nice little thing here. Let's get rid of this macro. We don't need that, or let's not recognize that as a macro. And we'll do this as mm.c11 for mogamath.c11 and mm.sh. We'll open this up and see if we can get this to run. So let's put this over here. So hopefully when I redid that formula, I didn't screw it up. So let's kind of see what we got here. Undeclared I, because I right there should be something else, shouldn't it? It should be, this I is going to be our pixel index. We can change that to pi. Now if we're going to do pixel index like this, why don't we kind of keep our consistency here and be like pi is this thing, and then we can keep our colons here like this, right? And Why not, right? Just make it a little bit more consistent looking, right? Okay, let's give that a shot. See, let's remove this extra space, though. Okay, so let's give that a shot. See what we got here. Log deck's uninitialized, huh? Oh, yeah. So we got all these values. Now what we really want to do is write this out in like a table. So let's kind of do that right now, right? So we're going to assume that we know what we're doing with the indices. But let's say that we don't. Let's do printf. And it should be like percent, what is it, 0D, I believe, for 0 in front of it. Printf percent 0D, let's give it a shot. So just do the pixel index, right? Let's just throw something in there and see if we can. I think without the printf we might set but not use. So let's throw this back in here really quick, because I don't want to worry about it right now. With that printf 0D pi, do we get the doesn't look like it. So let's look up the C, you know, print leading zeros. Percent 3D, space padded, 0 padded. So 0 3D, 0 3D, okay. So it looks like we're close, but instead of 0D, it needs to be 0 3D or 0 whatever. However many things we need. So 0 2D probably will work. Get rid of this. Nuke this because it's distracting. And put in a \n here so we can see what that is. See if we have our 0 padding. Okay, so we got our 0 padding there. And what we want to do here is we just want to print this, and then we want to printf just a space. And then after we print off that, we want to say, you know, if px, if 0 equals px, do a new line, right? Give that a shot, see if you can get like a little table going here of the indices. So we got the 0, but we kind of screwed that up a little bit, right? So the first thing we did a new line, and that was good, except that everything is kind of off here. So we really want we're kind of off by 1, aren't we? I think what we really want is, you know, if px modulus 8, if 1 equals px modulus 8, like I think we were off by 1. Let's give that a shot. That's probably not going to work either. That's still going to be off by 1 at the beginning, isn't it? Yeah, we're still off by 1, so you know what? I think all we gotta do to fix this is put this at the beginning. So we got 0 to 7, 1, 2, 3, 4, 5, 6, 7, 8, right? We got the 8s. Cool. So for this, let's try kind of like to do these loops multiple times. So we're going to take this and just do the for loop all over again, right? We're going to do the same for loop. And we had this px, py, we had the index here. But now we're going to try the same thing, but with a px, py, right? Okay. Is that how we want to do it? And this would be the easiest thing would just be, instead of pi, we do mogadex. And that's assuming we know, that's assuming that we're using the appropriate values in the first place. Uninitialized, huh? Well, it's... px may be uninitialized in this function. You see px here, we see it equals pi divided by this. Yeah, I don't know why it thinks that. Oh, this px here, though. Alright, because to get px, we gotta do... Alright, so we don't even need the y, do we? We just need to look at the x value. Px. Okay, let's take a look at that. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So we have some type of spiraling over here. There's a little spiraling pattern here. And then we're doing the same thing. I'm going to guess that kind of spirals in 4 ways, right? So after 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31. Okay, and then over here we probably have a spiraling pattern as well, right? So 32, 33, 36, 37. Yeah, so we have this spirally dude here. 48. Okay, so we have 4 little quadrants of these spirals. Okay, cool. So I see you have 4 main quadrants, each with a layered spiraling layered Okay, so he has like this zigzag pattern or something, and this has to do with the way he's laying out circuits, I think. How the wiring needs to work. So we can take all these index locations, we can remap them to I think this might be like these might be pin numbers or address. There might be addresses, linear addresses in an array. But now that we know that, let's look at this. And somewhere we should see some type of quadrant, right? So, when we have the x and the y, I think the first thing we need to know is what quadrant we're in. It looks like, hey, figure out what quadrant you're in. Divide by 4 times 32. Divide by x times 16. So that's interesting. So there's kind of a quadrant kind of thing here, right? We divide by x and gets a 0, 1, 2, or a 3. Or hold on. This division by 4 would be... that's not figuring out what quadrant we're in. We're saying 1, 2, 3, 4. 1, 2, 3, 4. No, that's what quadrant we're in. 1, 2, 3, 4. Okay. So yeah, so dividing by 4, because the quadrant size is 4. So... quadrant y-axis multiplied by 32. And this is the quadrant x-axis multiplied by 16. Okay, now why is there a 16 and a 32 here? Yeah, that's because, let's look at this. 56, 57, 58, 40. Nope, not quite. Things are kind of doubled here. I don't know why that's like that. There's an 8 by 8, so I don't know why there's this minus 16 here. Modulus 4, modulus 4, modulus 4. I have no clue. So what we could do is we could try to solve it ourselves. And, section. So we're going to try our math. We're going to try to reconstruct it. Rather than try to understand what that's doing, we're going to try to use our own math. And we're going to try to figure out what the hell he was doing. So we know that we got this nice little table. Let's copy the table from the output. And... Moga's table. So we have Moga's table here. And we can see that the first thing we have here is these 4 distinct sections. Excuse me. So you have 4 distinct sections here. Right, so... So I don't know how I want to do this. So this right here is still 0. And this is 1. I'm going to put this over here like that. So this is a 0. And... oh, I see. Yeah, I don't know. And this is a 1. So you got 0s and 1s. So we see those quadrants, then we see kind of this spiraling thing. And we know the first thing we need to do is figure out... we need to figure out what quadrant we're in, right? So int we have Moga Math. Let's just call this John Math. Int x, int y. And here we want to just calculate, well, how do we get these sections here? So the first thing is int quad x equals x. We had a division, right? We had this division divided by 4. So x divided by 4 int qy y divided by 4. So I believe that this is qy times 32 for some reason. This is qx times 16 for some reason. We don't know why. Yeah, so once we have these quadrants that we're in, we have to figure out so somehow there's an index to xy for all this. But okay, once we figure out what quadrant we're in, we need to figure out the local offset. So 0, 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4. It's a 4 by 4. It's a 16, right? So there's a 16 offset here. And where's our 16? We got a nice little 16 here. We also have this multiply by 16 over here. So, int q1. So, let's say q base. Or q0. Let's call this q0. And say that q0 equals 0, 1, 2, or 3, right? Which quadrant we're in. So we got to take the quadrant. We can see 0, 16, 32, and 48. So we need index to xy to index. Okay, and the index so define num quads is 2. So quad span is 2, right? It's a 2x2 outer quadrants. And then down here we're going to undef that. So undef quad span. Okay. So we're going to take this QY. And this is our QX. And this is going to be QI. So int use tile map collision math to figure out which 4x4 which main subcell which of the 4 subcells we are in. Each subcell, it measures 4x4 pixels / LED lights. Right? So that's what's going on here. Then run an index to an xy to index formula to get the 1D representation of the quadrant location. Right, so that's what we're doing here. Once we have that quadrant location, it looks like we're going to add, we're going to multiply it by 16. So 16, right, so 16. If we add another 16, we get a 32, we get a 48. So equals Qi times 16. So this is Qi this is also Qi. And over here is also Qi, right? Alright, so we have these different Qi's depending on what quadrant we're in. So we got Qx, right? So if I want to talk about Qx, this is Qx. This is Qx0. Then over here is Qx1. Right? And this 4 is completely wrong. We can see the quad span right here. So why are we dividing by 4? No, we're dividing by 4 because there's 4 kind of things in here. 0, 1, 2, 3, 4, 5, 6, 7. Right? So, you know, assert x is greater than or equal to 0 and x is less than or equal to 8 minus 1. And assert y input chords are over an 8x8 tile map. Okay. So, no, this is correct. let's remove this here, this quad span here. So quad span is this thing. Actually, no, let's do this. Quad span is this. Quad span is equal to exactly 2 here. And this is we could call this LED span is what we could call this. So we could call this you know, so LED span equals 4. 4 by 4 pixels slash LEDs per quadrant. Alright, so that's what's going on there. Okay. And Q0, we have a Q0, right? Oh, we did QI. That's not correct, is it? This is Q0 here. So another thing is, we have a thing called QI. QI equals 1. QX equals 0. QY equals 0, right? So, so schematically, when we're looking at this, we have something like this. Zero, 1, 2, and 3. The X is 0 and 1. The Y is 0 and then 1 on here. And here, the X and Y are both 1, like that. Right? And this is still quad span here. So that's still quad span. And this is still LED span. Okay. So with that, we can, you know, assert QX greater than or equal to 0, and qx is less than or equal to 1, right? It's between 0 and 1, same thing with the y. And assert that qi, right here, qi is between 0 and 3. 0, 1, 2, 3. Okay. After we've got that, we got this q0, which is base value of our snake. Alright, so we have this, like, get first index value of our snaking LED pipe. Okay. That's what Q0 is. Right, these indices now. Now we have this kind of wrapping thing, right, where we are kind of remapping everything somehow. And it looks like the first thing we're doing is we're taking scanline order and we're turning it on its head here. Yeah. Okay, I'll be right back. I gotta take a break. I'm gonna stop recording and get back to this in the next video.